So let's continue where I left off early in the morning. Well, your brains have been fried with more large-scale structure and galaxy evolution. And so maybe it's good to sort of recap a little bit this picture, because when I ended, we were talking about lensing by galaxies, and so that's also this picture. This picture I usually use to sort of convey when we look at lensing by large-scale structure in this sort of most direct way, right? Because as light travels through the universe, it encounters structures, and so light rays that initially were uncorrelated get coupled. They show correlation in their apparent shapes because they experience similar tidal torques, right? Because the light beams get tidally torqued. And so galaxies that initially were randomly oriented, by the time we observe them in our telescope, we expect to see small correlations in their shapes. Of course, this is grossly exaggerated, but that's the principle. So by just looking at the correlations between galaxies, we can learn something about the statistics of the matter distribution. That's what we'll focus on. But you'll also see that these diffractions, they occur at very specific locations, at the high-density regions of the cosmic web. And therefore, if we can localize those, like in clusters or like in galaxies, we can actually cross-correlate those shapes. And so that's basically what this galaxy-galaxy lensing is about. And as I said, like galaxies do not come along, so we have to take that into account when we measure the lensing signal in larger and larger scales. And so a very convenient model, at least also to get some intuition for how things might play a role, is the halo model. Right? So I think we're reaching a level of precision that this no longer can be used to really model the data, but nonetheless it's a very nice tool to explore, because it makes explicitly, or it allows us to make an explicit difference in a statistical sense between galaxies that are the host or central galaxy of a halo and the satellite of a halo. I think that is a picture that has become very clear. When you look at a galaxy, the first thing you should ask, is it the host of the halo, is it the boss, or is it a satellite? Because if it's a satellite, its evolution has been somewhat different from the host. It tends to be quenched earlier. There tends to be the dark matter halos are expected to be tidally stripped. Things we want to measure, of course, but that makes a difference in the signals we project, because we need to assume density profiles, right? Because we want to predict the lensing signal in this case, and we have to distinguish between centrals and satellites there. Then you need to sort of say, okay, now I have that distinction within a halo, but how many halos do I have, and what are their statistical properties? So there you can look at sort of prescriptions for the clustering of halos, especially if you have a mass function. If you have the bias as a function of mass, you can do this statistically. And then sort of related to the once you have these halos, you have to say, okay, there must be a central in there, up to down to some mass. And you have to define how many satellites you want in there. So that's what we call the halo occupation distribution. It's a statistical description that when you have a halo of a given mass, on average, there will be so many galaxies in there, and you can go a step further, you can say the distribution around that mean value can be Poisson, can be sub-Poisson, etc. So it's all, in a way, encoding information in a very statistical way, which ultimately should be predicted by a model of galaxy formation. And it takes a very simple stance that all dark matter is in a halo, which we know is not quite correct. So it's exactly in that transition regime where we have to sort of look at sort of the large-scale structure. We have to keep that in mind. And so that's the picture, right? So this is what you get in an Ebola simulation, and the halo model is essentially the cartoon version of that. Basically, every density, every halo above the threshold, you just assign, you make it a ball. Of course, we know halos are triaxial, so it's a very much simplification, but in a statistical sense, actually, we can go a long way. And so then you have in that halo galaxies, the central satellites, and all kinds of properties that you assign to them. And then, of course, we want to do lensing. So what we're doing in lensing, we're stacking things. And this picture then shows what I said earlier. When you're stacking, you have to be thinking about how to model it. Because here are a bunch of, right, these are all halos in a halo model. They have a central, sometimes the central is blue, sometimes it's not. And so, for instance, if I decide to stack blue galaxies, you can see, so I take all the blue galaxies in the sample, you see that I'm doing something very complex, because in this case, the blue galaxy is the central, in this case, it's satellite. So when I stack samples of galaxies, I'm actually combining satellites and centrals at the same time. So if I don't have prior information about those, I will be observing a mix of those. And the same would be true for the red galaxies if I pick that. I also end up having a mix. I can try to sort of pre-select things so that the interpretation is simpler, but in general, the interpretation of that stacking signal is complex. I really need this model. I need ways to assign different kinds of galaxies, because really at any point I will be stacking a whole bunch of things. And this is an older result I showed earlier, also the result for Mobility, but this is an older result with we have a nice decomposition. And you see, as a function of stellar mass, you see that these signals, as I said, for blue and red galaxies, can look very, very different. High stellar masses are only red galaxies, but over here you see that they're completely different behavior. And that is the result of the stacking, because the mix of central and satellite galaxies is very different. So I'll rush through this quickly because it's not that important. But basically what we have is, like, we describe this lensing signal, this delta sigma, as a model for delta sigma for the centrals, and we assign in a probabilistic way, like given a halo mass and a luminosity, we assign a profile, and so let's make this an NFW profile, we can do all kinds of things here. And we explicitly specify that we're also adding satellites with a certain probability. And so this ratio of these probabilities says something about the satellite fraction, right? What fraction of galaxies are satellites? So the sum of these should add up to 1. But we also explicitly make clear that satellites can have different profiles, which is actually something that is not well constrained observation, and there's even some discussion on the numerical convergence of this. So it's a very important test to also be doing. And on top of this, we have to account for the fact that if I have a galaxy here, there's an excess probability there's a galaxy somewhere nearby. Well, that excess probability is determined by the galaxy bias in the mass. And so there's an additional set of terms which we call the two halo terms that model sort of that large-scale behavior in this kink that we saw before. So yeah, I don't want to go in too much detail, but as I said, we need to populate, we need to assign galaxies to these halos. And something you often see is people call or define what they call a halo occupation distribution, or HOD. So they literally say the number of galaxies as a function of mass is this much. But in a way, a more, in my opinion, somewhat elegant way is to use the conditional luminosity function, because we know observationally that when you look at clusters, when you look at groups, when you look at a field, that the luminosity function itself is well described by a Schechter function. So we're already putting a little bit more knowledge into the modeling, and that's in general advisable, right? You can treat a problem completely statistical, which has unfortunately become a little bit common in cosmology, where people almost forget that they're looking at a physical system. And all the physical information you have about a system, you should try to incorporate. Sometimes it's very difficult, but that really should be the main motivation. And so this luminosity function is nice because, again, we can use Bayes' theorem to relate all these things, and basically we can just use observations to sort of motivate these halo occupation distributions. And then again, what we see as a result is that we see a combination of these halos. And actually, when we think of probe combination later on, some of these ideas will come back. But actually, this is how some of these models that we want to apply to the future data sets actually try to constrain cosmology, because effectively they will ultimately try to. Yeah. Right, and so you can basically have a prescription for the luminosity function. You also need something, either the correlation length or the bias parameters. You need also a model for galaxy biasing in this case, because once you look at the moment you look at galaxies, you need to think of galaxy bias, and actually in this case also formally the cross correlation coefficient, because we'll look at a cross correlation. This cross correlation large scale should be 1, and there's a physical argument for that, because galaxy formation does not know so much about its large scale environment. So whatever statistics you get must be correlated with the matter statistics. But on small scales, deviations from very simple direct linear relation between dark matter and galaxies can lead to deviations. And so these halo occupation distributions can be quite, it's very slow. Yeah, oh, now I went fast. So, go back. Okay, so basically what you get is that here you see then the corresponding halo occupation distributions, and usually they are quite complex at low masses, but then you can have one galaxy in a halo and very few satellites. But when you look at the central, so usually you see that these central distributions are sort of bumpy log normal distributions, and then the satellites are this sort of power law distribution, so that as you combine things, you end up with this Schechter-like field. But so, these are details, but basically these are models that you then try to constrain the parameters of by combining the data. And then what we're doing, so again, the details, but the simple picture is you have a prediction for what we call the one halo term, so that is this mix of centrals and satellites. Right? You have all kinds of parameters that then specify what the lensing should look like, and then you have a biasing model that then effectively predicts the two halo contribution, which will dominate on large scales. And then you put it all in a mix and try to fit the data. As I said, so an interesting question is how to model the satellites, because observationally there is very little direct evidence, because the measurements are actually notoriously difficult. I've been trying now for 15 years or so to measure it, and I think I know how to do it, but really the benefit is once we do the modeling with Euclid. So Euclid will really be a major step forward in also directly constraining some of the tidal stripping of dark matter halos. But also we're looking at the star, so we're actually looking at the intercluster light, something we're working on actively now. But yeah, so you get all these models, forget the equations, let's look at the curves. You get all these different contributions here. So this is one of those signals we saw before from Belander et al. And you basically have a contribution for the stellar mass in the galaxy, so essentially we're not very sensitive to this. But you see in red the contributions from the central, so the starlight, the halo, and the two halo terms. So these are basic contributions from other central galaxies that are clustering with respect to the centrals. And then here you see all these satellite contributions. Again, on small scales, you see the halo of the satellites, but you see also these bumps because these satellites are all within a halo, and you tend up adding the contribution from the main halo over and over again, but in a miscentered way. But so you can get all these curves, you pre-compute them, and then you fit all their model parameters, and then you get these kind of solid curves that you see here. Right? So and these measurements tell us something about the mass, given a stellar mass, but also something about the satellite contribution. So they say, well, this is the mass as a function of stellar mass, so that's something quite interesting. But you see also here, we get information about the satellite fractions. And so what we find is that when we look at low mass or low stellar mass red galaxies, they are almost always satellite galaxies. Right? You see the satellite fraction to fit the signal we basically find that it's consistent with satellites only. Whereas if you go to high mass, we eventually find, well, first of all, that the blue galaxies are almost always centrals, and that tells us something about galaxy formation. Blue galaxies do not survive long as satellites. They tend to get quenched by the tidal effects and other harassment. But you see that the satellite fraction declines as you go to higher mass. And we can do a lot more, which is very, very difficult to do this right, but it's possible to combine clustering, right? Because after all, we know the spatial distribution of these lenses. So you can combine clustering with constraints on the luminosity function and lensing, and that really breaks many of the parameter degeneracies in these models of the halo model, and also allows us to constrain the distribution, so the widths of these relations, because we have these scaling relations, but we also need statistical prescription, because if you take a halo of a given stellar mass, there is quite a large range in halo mass associated with it. So it's not that the relation between halo mass and stellar mass is 1-to-1. There's a large scatter, a log normal scatter of about 0.3, 0.2 dex. And actually, it's probably also mass dependent, but it's a significant scatter. If you take a galaxy with the same given luminosity or stellar mass, there's about a factor of 2 difference or variation in halo mass. Right? So we're measuring the average, but we still need to account for these subtle differences. But yeah, so you can do this, and actually a quite interesting result is then, so this is already a little bit old, but you see that when you look at this halo mass over stellar mass, right, if you take a huge part of the universe, including baryons, that gives us a sense of the efficiency of star formation. If we start off with a cosmic density of baryons, a fraction of those gets converted into stars, and we see that, and we knew this already for some time, but this is a very direct way, that around L star, like on Milky Way, star formation is most efficient because there's a relative, in this case, the highest fraction of stellar mass given halo mass. Right? And we see that as we go to lower mass, actually those, so a high value means here dark matter dominated, but as we go to low mass, these halos have relatively few stars. We think that's supernova feedback that basically dries the gas out and therefore prevents star formation to be efficient. Over here, so the clusters and groups, we think it's AGN feedback, but anyway, regardless of what is happening, there are physical processes at play that make sure that around this D, around L star, star formation is most efficient, and we see this in a very direct way. And so that's sort of wrapping up the galaxy lensing applications, where we focus more on make the link to galaxy formation. Bias itself, so when people do cosmology with galaxy clustering, lensing measurements can provide direct measurements of bias. That's something that's been done. Something I haven't talked about, I did work on it. Again, a very difficult measurement is actually look at the flattening of dark matter halos, because that's predicted by cold dark matter, and these axis ratios are ways of testing the dark matter paradigm. They also rule out modified gravity theories that don't require dark matter. And you can go a step further, you can look not only at the two-point function, but you can look at higher order correlation functions. So there's a lot of unexplored potential in all these measurements. Right? But I think what is very important, and that is relevant for the next part of the lecture, is that we can do cosmic shear, so we can do the shear correlation function. It's fairly straightforward to interpret, but if we really want to unlock the potential of these future surveys, we really need to link the galaxies and the dark matter. So really, this is where this galaxy lensing and the properties of galaxies becomes ever more important. So we're actually, the whole field is moving towards incorporating these clustering measurements, and effectively what the role of lensing changes into setting the mass scales, basically defining how galaxies populate dark matter halos empirically, and once you figure that out, you can do cosmology with galaxies. right? But if you then look at the projects that are coming online, they're largely driven by this desire to measure the shapes of galaxies, or something we call cosmic shear. So cosmic shear is where you say, I'm not going to pre-identify locations where I measure things. I just have my galaxies, and I know lensing distorts the sky and therefore induces correlations, apparent correlations between the shapes of galaxies. And so it's observationally the most challenging of them, so this is why a lot of focus on the technical development is focused on that, because there are all kinds of observational effects that are orders of magnitude larger than the signal we're after. Right, so you look at a galaxy, I do a measurement, you have no way of telling whether the measurement was unbiased, because the signal to noise of each measurement is maybe 1%. Right? So it's only when you average many things that you get a sense, oh, this went well. But it's only once you do that. Also, as I said this morning, right, we need to figure out the geometry. So if you want to get this signal out, because things were very noisy, we need photometric redshifts, because we can't get spectroscopic redshifts. So we need to actually really calibrate this. And actually very important, and I'll focus on this mostly, is that it's both a blessing and a curse that there's a lot of information in the sort of small scale, the nonlinear part of the power spectrum, but it's also very hard to interpret. So we're mostly sensitive to nonlinear structure formation. So very briefly, making the link to what we did. So what we saw this morning is, well, we have this gravitational lensing potential, and so now we basically say, we now look at a random part of the sky. And so what is that quantity then? Well, that's basically an integral of the gravitational potential along the line of sight. So what we did this morning, say, oh, here's a cluster. It has a surface density, and I need to multiply or divide by the critical surface density to get a convergence. So I had this combination of angular diameter distances. That's the same here. This is a function of the angular diameter distance for arbitrary cosmology, so that's why it's written this way, but this is essentially the same DLS over DS and DL. So this is sort of a measure, when you combine everything, it's effectively this critical surface density, and you're adding up all these contributions. So we're making the assumption that when I follow this photon goes through the universe, that it can simply sum up all the contributions from these gravitational potentials. And so that's an important approximation, studied quite well, because indeed the deflection angles are very small, so this actually works. So basically I can just integrate along the line of sight and build up the statistics that way. And so this was in potential, so again we can relate things to convergence, etc. So when we look at the power spectrum density fluctuations, we basically look at overdensities. So the equivalent, basically using the Poisson equation, we can relate the potential to the density, and when we basically plug that into the previous equation, we can basically say the convergence as a function of distance and position on the sky is this kind of integral. Like, we don't know necessarily what the overdensity is, but this allows us to start building up the statistics. So basically, again, we're summing up all these contributions to the lensing signal. That's all you need to remember. So you have here the overdensities, and everything gets weighted with this lensing kernel. So that basically is like a filter in redshift, if you wish, that tells you where you're most sensitive. And so that's what you can fold in. So we can, instead of these distance, radial distances, we can put in redshift distributions. Again, the details do not matter much, but the key is, of course, how are we going to relate this to something we can measure? Because this is all very nice. I can, in principle, compute this, at least the statistics, but how do I relate things to shear? And it turns out there is a way to relate it to, because if you have right? So we typically assume, especially on large scales, that this field of overdensities is a homogeneous and isotropic random field. In 3D, because we have all these projections, so we can, doesn't matter which way we view the universe, that is true. And that turns out that is also true for 2D. So we can write, basically, if you have density fluctuations, we can write a correlation between these quantities. So there's a 2D projection, right? We have the densities, we integrate along the line of sight, so that gets us our projected, so surface density or lensing weighted surface density or convergence. And we can look at the correlation between those. So we look at two positions. If everything is random, of course, the correlation will be 0. If there are correlations because of structure, it will not be 0. And so basically we have this cross correlation, and because of isotropy, this can only be a function of the difference. And this correlation function has a power spectrum, which is given by this quantity. So this is sort of the standard relation between power spectrum and correlation function. You can measure a correlation function, the data, and then convert it into a power spectrum, or you can estimate a power spectrum from the data and actually figure out the correlation function itself. So they're basically like Fourier transforms of each other, transforms of each other, as you can see here. Now it turns out that a convergence is really that kind of quantity, so we can use the math of this Limber approximation and express the convergence power spectrum. So if we look at the sky and somehow could see convergence, we would compute the correlation function, the power spectrum of the convergence of the sky. That power spectrum is directly related to the power spectrum of density fluctuations. So this is what codes like CAMP predict. So from a fundamental theory of, like, so an inflation model with sort of that evolves forward, or an embodied simulation, you can measure these things. They will give you this power spectrum as a function of scale and redshift. Then there's this geometry that is always there in lensing, and then some additional parameters, but we can relate this in principle. So now we know. So if we had now the convergence power spectrum, we could learn something about the matter power spectrum, and that tells us something about cosmology. But how do we get to convergence? Right? Because that's not really something we measure. We could measure with magnification, but I hopefully convinced you this morning that that's not a good idea. But of course, by taking this notion of mass reconstruction, convergence and shear are related. Because shear is something we can measure. And so again, you see this here. Wherever I have high convergence, I see very strong correlations in the shear. So the question is, could we relate the two? And it turns out that, and of course we know this already, that shear and convergence are related. But it's even better when we look at these density fluctuations, because you can use the same analogy which I did this morning when I derived this Kaiser-Squires mass reconstruction, but you can write the convergence in Fourier space, then it's very easily related to the power spectrum, but I can then in the end get this expression, because again, I can also express the shear in terms of derivatives of the potential. And so this is a different way of saying that what we saw this morning, this mass reconstruction, in Fourier space, it looks like this. And I can rewrite this in this way as basically a complex power and an angle. And that's interesting because, of course, this, okay, doesn't seem obvious, but if you look now at the power spectrum, you'll take the modulus of this, but this has a modulus of 1, right? So basically, the convergence and the shear, if you look back here, right? So I take the correlation function of this then becomes 1, and I get 1 times the correlation function of the convergence. The convergence and the shear have the identical power spectrum. So all I need to do is measure the power spectrum of the shear, And for free, I get the convergence power spectrum of the convergence power spectrum, which means I can directly relate my observations to the matter power spectrum. That is the power of weak gravitational lensing. There's no galaxy bias in there. It's a very direct measurement. Right? This is what motivated people to explore this, because we don't need to know anything about galaxy formation to do this. And so what we then get is effectively what we're measuring to first order is how clumpy is the universe. So we can have a little bit of matter fluctuating a lot, so that's the top one, or a lot of matter, so high omega matter, low sigma 8, and we have a hard time distinguishing between the two. So this is when you look at a plot of sigma 8 versus omega matter, that lensing measurements show these very big bananas. Right? There's a degeneracy. And the degeneracy roughly is something like this nowadays. So this S8 I've been talking about, we pick omega matter to the 1.5 times sigma 8. And it depends on redshift. And that's actually what we're using by splitting by redshift. We can break some of the degeneracy. Because these bananas rotate a little bit with redshift. And once you combine many bananas, in the end, you end up not with a banana, but with something, an ellipse or something round. So different fruit. And that's basically by using the information, the redshift information, distance information to the sources. And one way of sort of visualizing it, even though that's not what we do, is that if I look at my most distant galaxies, they see all the matter from redshift 0 to very high redshift. But if I now look at my low redshift galaxies, they don't know what happened at high redshift. So I can make sort of pictures of the mass distribution, and as I march up in redshift, I see the sum of what I have at low redshift plus the new stuff. But if I knew what was there at low redshift, I can sort of subtract off that contribution and see at any redshift what is the new information that is being added. So I'm using really all these correlations between different redshifts to get a sense of how structure grows. But still, it's limited because this lensing kernel is very broad. So that's good because that allows us to use photometric redshift, so we don't have to localize galaxies extremely well along the line of sight. But the price we pay is that actually so we want to measure the growth of structure, but basically it's like we see in the radial direction, extremely blurred version of the universe. And also, if you look at this power spectrum as a function of scale, we're seeing dark matter. And dark matter has a very boring power spectrum. No wiggles, no features, very few features. And so this is why, the information content is still somewhat limited. Right? Because you see that if you take galaxies and split them in half, you really get independent information for high and low redshift. If you look at at the shear signal, you basically see that the highest redshift sample gets more information from high redshift, but there are strong correlations. I think there's overlap with what is happening in the low redshift. And so this is, by slicing the universe, we can compare these power spectra, but it turns out that if we slice it in more than 5 or 6 bins, the information has saturated. So that's basically the result of the fact that we have this very poor resolution along the line of sight. By the time we can keep slicing as much as we want, but basically we already have the information. The overlaps have become so large that we can't do much better. But still, by doing tomography, if we can really separate these samples, we can break these degeneracies between the normalization and the matter density and really test measurements of growth of structure. In particular, and this is what works quite well, measure the properties of the dark energy equation of state. So this is what is driving these lensing measurements, because weak lensing is, at least on paper, the most powerful probe of measuring dark energy equation of state. And as I alluded to yesterday, we can also look at GR and cosmological scales. But this is really the big science phase for Euclid, although we get all the other things for free. So this is what I was said before. So you can basically slice in ever more bin, and you can look at the error bars of your parameters, and you find that once you hit 5 bins, the information, you basically get the error bar doesn't shrink anymore. And it's because you're just adding redundant information by slicing things further. The information is already saturated. Still, if you look at Euclid, we're actually planning to do 10 bins, and I'll get back to that why we want to do this, because from the lensing only perspective, it doesn't make any sense. But, of course, we want to use the galaxy information, and the galaxy information can be sliced much better. So as I said, also one complication is that we're measuring, so on large scales you can literally compute the power spectrum from first principles. Or you can use perturbation theory to make the prediction. But on small scales, these halos collapse, orbits cross, it becomes difficult, if not impossible, to really make a clear prediction what the power spectrum should look like. So we're using embodied simulation to make these predictions. And that's what you're seeing here as a function of angular scale, of angular wave number, that here is this is what you would measure in a simulation, so the nonlinear power spectrum. And here is the linear power spectrum. And so you really see what a big difference nonlinear structure formation makes. Right? So you get an order of magnitude more power on small scales because stuff collapses. But it actually complicates the analysis because on these large scales, all the modes that were imprinted in the CMB, they evolve independently, so they're nicely uncoupled. So all these modes give me information about the initial conditions of the universe, which is of course what I'm after. But once these modes get coupled, once you start collapsing structures, making dark matter halos, that information effectively moves into the higher order statistics, which are very difficult to predict. So this is where I think in the coming years you will see a bigger and bigger role of embodied simulations, and in particular emulators, to sort of extract that information that is in the data, because the amount of information, the 2-point correlation functions, because so far I only looked at a galaxy, or a position of a galaxy and a shear, and the shear of a shear, but a lot of information is when we look at triplets, like shear, 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 galaxies with shear, shear, galaxy, galaxy, and shear. So all these higher order correlations, I can do shear, 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 and they all contain information that is being moved to these small scales, encoding information about structure formation. Or actually it turns out in very efficient ways to actually look at peaks. But again, this is an area of active research, how much information can be extracted from these small scales. But it's clear there's a lot of information there, but it's also, where it gets very annoying, because baryons, yeah, they are being kicked around by various astrophysical processes on these scales. So on very large scales, I can approximate the astrophysics by an effective bias parameter. I can try to approximate. I know that on average things should be more or less the cosmic mean. And so basically when you look in two different simulations, one a hydro simulation with no feedback, one with supernova and AGN feedback, you see that the positions of the peaks are more or less the same. So when I look at the large scale clustering, baryon physics doesn't do much. Of course it changes the luminosities of galaxies, but that's basically captured by changing the bias prescription. But the positions of galaxies do not move because an AGN goes off or a supernova goes off. But you do see that on small scales, that the total matter distribution, what you see here is the gas particles, that the gas particles are distributed quite differently when I have AGN feedback or not. And this is sort of the scales where lensing is most powerful. This is where we really get a lot of the cosmological information. And so we are actually, even though the measurement of lensing is direct and is a very good measurement of the matter distribution, the problem is that our predictions, the theory that we're comparing to, is actually uncertain because of our limited knowledge of galaxy formation and varying feedback. And so you can then say, okay, and this is where this halo model comes in. I can actually use the halo model to make a prediction for this nonlinear power spectrum, because I can just say, okay, I have a mass function, I have a lensing signal, I can add this all up and I can compute the power spectrum. And then you can play a little game. You can say, okay, if I take halos within a certain mass range, how much do they contribute to my power spectrum? And what you then find is that that's sort of indicated here as a function of scale, which halo masses contribute. So you see on very small scales, that's high K, is low mass halos. Right? Galaxies are numerous, but not very massive, so they don't contribute much in general. This is the scale where lensing is most sensitive to, sort of megaparsec, 10 megaparsec scales. And when you see, then you see that it's mostly 10 to the 13, 10 to the 14, solar mass systems maybe a bit higher. It's galaxy groups. Galaxy groups are the most common structure. Most galaxies in the universe are in a galaxy group. We are in a galaxy group. Right, so this is the most common structure, and this is for lensing, for cosmic shear, the dominant contributor to the signal, because groups are both common and sufficiently massive to actually give you a signal. Clusters are supermassive, but they're rare, and so that's why eventually their contribution is not that important. And so you can play it again, and so basically you can say, okay, if I now look, so if I look at basically what is the gravitational binding energy and the energy output of an AGN, you expect indeed that there might be trouble. Because in a galaxy group, an AGN can do quite some damage. Of course, in galaxies it does a lot of damage, it blows a lot of the baryons out, but the galaxy did not contribute much. But in galaxy groups, gas gets redistributed, that's what you saw in the picture before. And also, if you look at hydro simulations, as a function of mass, you see that if you play different feedback models or different models for the power of the AGN feedback blowing out gas, you can see that the gas fractions, or a measure of feedback, at high mass, not much happens. Because the halo is so massive, the AGN can redistribute gas a little bit, but it gets stuck in the middle, it can't get out. But in groups, you see the different feedback models, the different colors here. If you crank up the feedback, that in this group range you get very large differences in the gas content of these groups. And although the gas is only 15% of the total matter distribution, when we start doing dark energy measurements, the effects of dark energy, we're talking percent differences. And so screwing up half of that 15% is overwhelmingly significant compared to the small changes in dark energy we're after. And so when we then look at this power spectra compared to the dark matter only one, this is all the work we've done. When we put this on the map, you can get very large differences in this, exactly in the regime where we're most sensitive with lensing. So the gas gets more or less randomized and suppresses the power spectrum compared to what we would have naively predicted from our model of structure formation. And this is just to highlight the point. Let's focus on the dark energy equation of state. This would be the truth, but if we forgot about AGN feedback, we would conclude that W is less than -1. It's something like -1.4 for Euclid. Then theorists would write tons of papers about all kinds of new physics, but actually it's because we don't understand what happens to ordinary atoms in our universe. Right? So this is something to watch out for. So even though the measurement of lensing is a direct measurement, it's insensitive to the composition of the material, the interpretation is very sensitive to this. And the way forward, of course, we can parameterize our ignorance, but of course this leaves observational signatures in the relation between the dark matter halos and what we can observe about galaxies. And that's something we can measure. So we can try to measure the scaling relations that I showed earlier, the relation between halo mass and stellar mass. We can look at X-ray luminosity and halo mass and try to constrain these models of galaxy formation to ultimately get to sort of the modeling of that effect. And in principle, with even simple models, we go a long way to recovering the correct information. So that's really something, an area of active research. People are very worried that this is limiting the precision of future surveys such as Euclid and LSST. But that's the idea, is that with better priors, we can sort of home in on the correct prediction. And there's another source of bias, which is more related to also the tidal torquing that you've heard about, I think, from Riem. But I think that's something we can leave until after a short break. So let's break for about 10 minutes or so and then wrap this all up. Okay, so let's do the last bit of today. A topic that really connects some of the issues with cosmic shear and actually a really old question in galaxy formation. This question goes back to when Hubble saw spiral galaxies, and you look at them and you're like, why are they rotating? Right? And it has to do with angular alignment. So where does the angular alignment come from? Is angular momentum aligned? Is it a result of structure formation? And it's clear now that although you can make predictions for dark matter halos, the tidal alignments, that when it comes to galaxies, the situation is more complex, again, because of complex baryon processes. So in the long run, they may align, but galaxy mergers really screw up some of these initial alignments that may have been present. And we also see this in data, that the alignments depend, the strength of the alignment signal depends on the scales of where you're looking at matching the shape of the galaxy. And so these intrinsic alignments are annoying though, because they confuse or they sort of complicate this basic assumption that we started off with, that when we see a net correlation in the shapes of galaxies, that's the result of lensing. And so what we measure in reality is a combination, because you can have here lensing, so these are distant galaxies, they are nicely sheared, but here are satellite galaxies of this green central, and they are actually radially aligned due to tidal torques, and basically what we're getting is a complex interplay of, for high redshift galaxies, a alignment signal, but when we do cross correlations, we see also anti-correlations because this intrinsic alignments start coupling with the shear. So what we measure in reality is not just the lensing signal, but also the correlations between the intrinsic alignments of galaxies, and they have to be at the same redshift because they need to be tidally locked together, of course, but it's something we call the II contribution, intrinsic. But the real nightmare is this GI contribution, where the shear at high redshift couples to intrinsic alignments at low redshift. So we're really getting a very complex redshift dependence of these contributions. And if we ignore them, just like the case for the baryon physics, we basically would end up with completely incorrect cosmological parameters. So again, the measurement of the lensing signal is fine, but the interpretation of the signal is complicated by not only AGN physics, but also by an even more fundamental question in galaxy formation than these tidal alignments. But again, we can try to measure it, and this is work done with a PhD student from mine that recently graduated, because we can say, okay, these alignments must come from galaxies that are physically close. And so let's now find in our surveys galaxies that are physically close, say red galaxies. And indeed, we can look in groups to see if the satellites are aligned, and we see a tiny bit of alignment on very, very small scales. Typically, we see nothing for blue galaxies. And again, this is consistent of maybe something for the most luminous ones. For blue galaxies, for blue centrals, the alignment signal has yet to be detected. Also, the predictions predict that it's a second-order effect. It's a alignment of the spins, not of the actual shape of the galaxy distribution. It's a different mechanism that gives rise to the spin alignments, which is second order and at a level that we cannot see yet. But when we look at red galaxies, we can see, or the alignment signal has been detected for luminous red galaxies in Sloan. We've also done measurements with gamma, but we actually extended the measurements photometrically to lower masses, and something very interesting started to appear, because all the measurements were dominated at high mass where the alignments are very strong. This goes back to the 80s, where Bingley looked at the central galaxies in clusters and found, if you want to find a cluster, just follow the direction. You find one cluster, the orientation of that central galaxy will point you to the next cluster. They were strongly aligned, and at high mass, these tidal alignments are very strong. But of course, most of the galaxies we use for lensing are over here. And so the question is, what's going on at low luminosity? And basically what we're finding is that there's actually appears to be a kink here. And that's interesting, because it sort of made sense. It put earlier results we had done with spectroscopic data in perspective. And so this suggests that although we now can predict the alignment signal much better, that actually the luminosity dependence might be more complex, until we actually did something else. Remember, like, this is a lensing server. We can look for the galaxy lensing signal around these galaxies and ask, okay, let's not plot this as a function of the luminosity, but of their halo mass, because we can measure it using lensing. So we use galaxy-galaxy lensing to basically convert these points to halo mass, and then, perhaps not too surprising, it becomes a single power law. That makes sense because this is tidal torquing. Tidal torquing gets determined by one parameter, and that's the mass of the halo. Right? If that tells you how susceptible it is or how much influence it can have. And so basically this kink here corresponds exactly to the features we see in the stellar mass-halo mass relation. So we think actually that at the end of the day, modeling the alignment signal, predicting the alignment signal may be a little bit easier than sort of this figure on the left suggested at first. So those are the complications. So now let's end with a more positive view, sort of like, okay, how do we do with the measurement side, the actual measurements? And so the cosmic shear had been the driver for the development of the technique, even though the first measurements focused on clusters to demonstrate the feasibility. But around 2000, in a period, I think in 2 days' time, 4 groups published their results. Basically, there was various teams in the world working independently and got remarkably consistent results. So I think this was one of the first indications for the turning points where people realized, that usually doesn't happen in cosmology. When 4 people publish a result independently and it agrees. Usually it's 2 people publish a result and it doesn't agree. Of course, that has changed now also a little bit, but really this people noticed. Of course, the error bars were large, so it's easier to do. But as I showed yesterday, we really come a long way since. We really have increased the amount of data exponentially. And we're really now starting to do 10 years or 20 years later, I would say we're now in the realm where we do cosmology. Right? So these clumpiness measurements are competitive with the Planck measurements, are the best available. And of course the next step is Euclid. And I think that is where we really are getting geared for. But it's interesting to sort of reflect back over the last period and say, okay, we had this exponential increase in data. That should mean that the error bar should decrease exponentially, right? Well, so they're decreasing now, finally, as you can see, but definitely not exponentially. Right, and that's the result of a better understanding, like the baryon physics that I talked about, like the intrinsic alignments that I talked about. And so over the years, as the amount of data grew, we also realized we had to take into account more and more computations in the data analysis. And so the net result is that actually the error bars have shrunk relatively little. Nonetheless, the measurements overall have stayed quite stable. So this is kind of encouraging. And so I like to joke that, so lensing cosmic shear is a complicated measurement. So many things can go wrong. And so at the end of the day, the central value theorem is your friend, because pretty much anything you do wrong cancels out with something else. Right? And that's sort of the indication here, that basically whenever we fix something or a bunch of things, things move up and down, but it can go either direction. And that's what you really see here. But finally, we're starting to see sort of converge, like basically error bars are shrinking compared to, say, 10 years ago. And this is what I showed yesterday. The gray line here is the Planck result. And so all these measurements are consistently below Planck. And so some of the measurements, or the project I've been working on is the kilodegree survey. So there's right now 3 main surveys doing cosmic shear. So kilodegree survey is completed, led by Koen Kuijken in Leiden. It's complemented by near-infrared data with Viking. So this is a survey that started a long time ago on the VLT survey telescope. It's next to the VLT. So it's also called the VST, which doesn't mean the very small telescope, a VLT survey telescope. And under the right, so there's a picture I think Koen taken, that it looks almost as big as a VLT, but it's considerably smaller. But it has a big camera. Right, so this has been really the driver for these surveys, is these large cameras, even though in comparison to the other project, this is now a small camera, and also especially to LSST. And so basically these are the fields we've targeted, and a very nice feature we did, we first focused on fields with a very unique spectroscopic redshift survey, the gamma survey. And that allowed us to, for instance, study these relations between galaxy mass and halo mass using spectroscopic redshift. So we have a lot of information. We have information about groups. So we're still working on using that information to improve models of baryon feedback. So it's basically targeting areas with interesting additional data, and it's been proven very, very useful. So this is sort of the early data. Then another large survey is a dark energy survey. So typically when you go to the US, you will hear not about KITS, you will only hear about DES, but here we're showing everybody's results. So that has a really large camera on a larger telescope, a 4-meter Blanco telescope, but it doesn't have the 9 bands that KITS has. And also the image quality is not as good. So the net result is, although they do 5,000 square degrees, we do about 1,350 square degrees. You see that, and I'll come up with a slide, that all these different surveys probe slightly different parts of parameters. So the different kind of sensitivities they are prone to. And then the really big beast is the Hypercimmerian Subaru, so that's the largest telescope, 8-meter telescope with a very large camera. And so they are doing an area that is similar to KITS, but because they're using such a large telescope, the data are phenomenally deep. They're very, very deep data. And the reason for that is actually not lensing related, it's actually follow-up spectroscopic survey, because it turns out for the lensing measurements, they didn't need to go so deep, because when you go so deep, you can't figure out what your source redshifts are. So the redshift calibration becomes an issue. So just taking deep data is not enough. So even if you can measure shapes, if you can't figure out the geometry, you still can't do cosmology with them. But nonetheless, it's pretty impressive data. So they're really very deep, and I used it yesterday also when I compared Euclid to LSST. It's an important test bed for LSST because the depth of the data is comparable to what LSST can reach. So you can really do a lot of tests, And in particular, something that is very relevant for LSST, sort of on the technical side, is the blending of galaxies. Once you're at that depth, you want to measure the shape of a galaxy, but unfortunately there's always another galaxy next to it. Always. Whereas in Euclid and kids, the situation is much less severe. So that's a problem we still have to deal with, but it's not as bad. And so this is kind of nice to see how they are very different. So both HSC and DS are prime focus cameras, so they hang in a prime focus, so they really suffer from typically quite large distortions. Whereas kids is at a Cassegrain focus, which means very small distortion. So certain systematics immediately get suppressed. We have the smallest telescope, that's bigger. Bigger is always good. Field of view is the biggest for DES. They also have the largest area, but I think what is very important, and I think that perhaps when we started the survey we hadn't fully appreciated this, but this has proven to be extremely valuable. The fact that we have near-infrared data, which allows us to extend the tomography to much higher redshifts. And these high redshift galaxies, they carry so much weight that effectively kids, when we look at the end of the day, our precision, it'll be comparable to DES. Because we can do this tomography much, much better. We also have better image quality, although Subaru is phenomenal in that regard. But you can see that, so although they detect 22 galaxies per square arc minute, they can't use many of them. So in the end, the depths become similar. And KITS is a small team. If you look at DES, although compared to Euclid, this wouldn't be a small team, or it would be a small team, but you can see the teams are getting bigger. So one thing we did is, like the earlier results, I said we focus on this area, and you can make these mass maps, but we haven't really done much with the mass maps, because as I said, the interpretation is much more complicated. It's much easier to keep working with the shear estimates itself. And so things that were improved and really made a big step forward was the inclusion of infrared data. So the first result did not include that, but as we moved forward, we kept improving things. So we went to the latest result, used 5 tomographic bins, but we're now working hard and hope by the end of the year that we can actually use 6 tomographic bins. And at 6, and we go from 1,000 square degrees to 1,350, so that's by itself is not much, but combined with that 6th bin, we can actually shrink our error bars by a square root of 2. So we're really making a big step forward. And this is the reason why these error bars shrinking so slowly, because we're adding more and more sophistication in the calibrations, the covariance matrix. So yesterday I ended with, when you look at Euclid and LC, everything matters. Already with kids, we're starting to see that game, like that we have to be careful how we compute our statistics. And so we're spending a lot of work, especially in Leiden, on calibrating the shape measurement algorithms, right? Because the power of lensing is that we can use the amplitude of the power spectrum. When you do it with galaxies, you have unknown bias. Lensing gives you this direct number, but only if you can measure shapes correctly. And that's really where a lot of the work has been going, and we now think we can do this with a precision of about 1%. And of course, as we move to Euclid, we need to do a factor of 10 better. But we also start with better data, so that helps. But really, is an area which has really taken off now. And so these are the latest results published last year. And in line with this plot that I showed, the values barely changed, but even though a lot of things changed in the analysis, the usual thing is like all this work and nothing changed, except for the error bar shrunk a little bit. And again, you see, so let's focus on the clumpiness, because here you see this banana that I was mentioning, right? This the fact that we have this degeneracy, so that's why we like to plot this S8. And again, you see different ways of combining or summarizing the data, but you see that, again, we keep being inconsistent with Planck. So no matter how we improve things, we still find that we're systematically lower than Planck. Then you can say, okay, what did DES find? Well, they are more consistent with Planck, except they were using photometric redshift for the calibration. If you use the same calibration as we use, which arguably is better, and we've added a lot of data since. So this, when you reanalyze the DES measurements using these better redshift calibration, you find that they are also very much in agreement. And so this is kind of interesting that so the sort of uncertainties in the current analysis are not driven by the shape measurements anymore, which people always thought would be the hard part, but it's how well can we figure out photometric redshifts. And again, that's where it helps with kids that we have really put a lot of effort there to calibrate that. But really the step forward, and it's coming back to what I said, the problem with lensing is the lensing power spectrum is super boring. There's no features. Along the redshift direction, we have this very poor, very coarse resolution. So the way forward is really to combine with clustering with the galaxy cross correlations, and that's shown here. So now when you go to lensing meetings, everybody's talking about 3 times 2 point analyses. And what they mean with that is that they're looking at the correlation of shape and shape, or shear and shear, shear and position, that's number 2, and number 3 is position, with galaxy clustering, photometric clustering. And so here we use BOSS, so it was spectroscopic clustering. But you see that once you combine data, that even though the clumpingness, so you basically S8, so this is the kid's lensing signal, the moment you combine with galaxy clustering and do the full analysis, you don't do so much in the amplitude, but you see you subtly constrain omega matter much better. And as we move forward, right, these parameter or these probe combinations will allow us to break the degeneracies in many parameters. And that's really driving a lot of the progress for things like Euclid, because this is a forecast for Euclid where a different version of, or actually more recent version of what I showed yesterday, right? You see that lensing and clustering by themselves are very powerful probes, but once you combine them, things go really, really well, right? You really shrink error bars by order of magnitude, right? But the only way we can do that reliably is if we can figure out how galaxies populate dark matter halos and how do they interact with their environment. So we really need to keep an eye on that aspect of galaxy evolution, which these data will provide tremendous information on. And something actually I plan to work on in the coming years, and actually got an ERC Advanced grant to explore that, is to really push to smaller scales. Because here you see all kinds of parameters, and you see that when you combine probes, like your error bars shrink compared to the sort of single probe cases. But what is more important is to compare left and right, pessimistic and optimistic. So I want to make, basically the goal is to make optimistic realistic by pushing to smaller scales, because then in certain parameters you can constrain things much, much better. But that means that the only way we can use these smaller scales if we get a better handle on this nonlinear structure formation and the astrophysical processes that complicate the analysis. But it really shows how much more we can get from these data if we can access the small scales and really try to actively pursue that link to galaxy formation. So that's really, I think, the main area of research in the coming years. Because these future data sets will give us the data, but they also give us the opportunity to tackle exactly those problems that are currently completely open. So already showed yesterday the Legacy Survey of Space and Time, very original, formerly known as the Large Synoptic Survey Telescope, but the telescope now has a name that I forgot because it's named after somebody from Microsoft, I think. Yeah, exactly. Yeah, you know it. But then the observatory is the Vera C. Rubin Observatory, or in short, Rubin Observatory. And then the survey they're going to do is the Legacy Survey of Space and Time, but they're going to do other projects as well. So that's a phenomenal project. As I said yesterday, 8-meter telescope like Subaru, and it's designed to just observe the whole sky, the whole southern sky, every couple of days. And that's changing, that will change the way we do astronomy, right? Because, yeah, you just download the picture. You're not going to go to the telescope and see what a galaxy looks like, you just download it. It will do photometric redshifts, and even though it will see many more galaxies than Euclid does, most of these galaxies are too faint or too blended to get accurate shape measurements. So when we look at the end of the day, after 10 years of LSST, the constraining power of cosmology is quite similar to Euclid. It's kind of fortuitous, it just happened to be the way, but it's quite, in terms of constraining power, remarkably similar projects. Another project a little bit further away, so the claim is, or their aim is to launch sometime 2025, 2026. So that's really, in a way, from space, the main competitor to Euclid. It's an infrared telescope, the Roman Space Telescope. It's actually a more versatile instrument. It's also way more expensive than Euclid. Euclid is of the order, if you count everything, of the order of €1 billion. Here you're talking several billion euros. But it can do a lot more, so it will do exoplanet work, but also originally it's designed to do some dark energy work, especially at high redshift. Again, it's a mirror the size of Hubble, so it's really a new kind of workhorse together with James Webb. But it will do a smaller survey, but it will be deeper using its strength. But of course, what I'm most excited about or worried about is Euclid. As I said yesterday, the launch date remains uncertain. So in a few months we hope to know more. But it's really this complete picture to test many aspects of the current model. So we talked about it yesterday already, so I don't spend too much time on that, and instead conclude and leave the floor for questions. But I hope to have convinced you that when we look at the current measurements, and especially the progress over the last 20 years, where basically we went from skepsis to sort of leading the way into the next decade, that we're getting excellent results. There's some interesting puzzles still, but it's very much a work in progress. And there's a lot of work that still needs to be done. We made a lot of progress in the last 20 years, but it's not that we're done. So as we move along, we keep discovering new things, but I think there are also very interesting opportunities. Data analysis is complex, and I think really what we've learned in the last decade is that when we move into the next decade for cosmology, observational cosmology, is that the link between galaxy formation and cosmology is becoming more and more clear. Sure, we can sort of throw away most of our data and get a unbiased measurement with a large error bar, but we should be trying to get the smallest possible error bar that we can still believe. Right? So that's really where the work is. But I think what is exciting is that as we move forward, and we keep solving the problems, and I think we're now at a stage that we have a very good understanding of what remains, and there's really no showstopper. In the case of Euclid, we just need a rocket, so if you have one, please let me know. Although not all rockets suffice. But I think it's a really exciting time to be working in this field, and so it's a good topic to be working in cosmology. And with that, I'd like to thank you and ask if there are any questions.